You're muted there, Wyatt.
There we go. Perfect.
Awesome.
Okay. Yes, thank you. As Liam said, I'm going to be talking about diagnostics of chaos in a system which does not have chaos. I'm a PhD student with Dr. Duncan O'Dell at McMaster University in Hamilton, and we're going to be talking about work that we also did in collaboration with Dr. Jesse Mumford as well. So let's first talk about what it means to be chaotic. So in a classical system, we often have this, this notion of chaos. It's the butterfly effect is a good measure of this. Essentially, that corresponds to an exponential sensitivity to initial conditions. So I can imagine I have some sort of phase space parameter or phase space some trajectory, and I perturb it slightly. It's going to have some sort of exponential dependence. So these trajectories are going to diverge with time. Often this is taken over some kind of phase space average, or maybe a thermal average, something like that. And in general, there are a spectrum of Lyapunov exponents, these lambdas, that characterize how fast these trajectories are diverging, but often they're just dominated by the largest one of these exponents. So any function of phase-space parameters will also inherit the Lyapunov exponent spectrum as well. So here I've just shown a Poisson bracket, which turns out to be pretty useful later on. You can use the Poisson bracket and show that there are some sort of exponential divergence of kind of functions of phase-space trajectories as well. The story in quantum mechanics is a little different. Because we don't have an exponential separation of trajectories, at least in kind of the state sense, because we have unitarity in dynamics of quantum mechanics. And so when we talk about quantum chaos, one of the classic signatures that's talked about is spectral correlations, which I'll get to in the next slide. And that's intimately related with random matrix theory. And another one is this object called the out-of-time ordered correlator, which is going to become very important as well. Essentially, it's what happens when you take the Poisson bracket to the quantum regime. And now you can start talking about some sort of exponential deviation of this object called the Poisson bracket, where the commutator, where you have the operators W and V, and it can start out either small or zero and then exponentially increase. There's a lot of hot topics associated with chaos that I'm not going to talk about too much here, one of which is thermalization, probably one of the most common topics. Chaos is the mechanism for thermalization. Which fights with localization and quantum antibody scars all kind of fall into the same story. We're not going to talk too much about into these topics. I'm just going to mention that they exist and people like to study them. So first things first, spectral correlations, as I mentioned before, as a diagnostic for quantum chaos. So you can imagine that I have some sort of Hamiltonian and I look at the level statistics of that Hamiltonian. So say, for example, I look at the level spacing, the difference between each level. And we check to see if that obeys a Wigner-Dyson distribution. The probability density function is Wigner-Dyson or a Poissonian distribution, and this helps us. Often we say, okay, well, this is chaotic if it is Wigner-Dyson, and not chaotic if it's something else like Poissonian. We have when I talk about correlations, I mean that in the chaotic case, the levels are correlated in the sense that you get level repulsion. So if you go look down at the spacing is down to zero, you see that there's a vanishingly small probability that there is a zero level spacing. And this is all well described within random matrix theory. So you can imagine if I have a chaotic system, it ends up being well described by random matrix theory, because you might have some sort of disorder in the system, and that leads to kind of a random matrix. There's a question there about the OTOC growing exponentially. Is that true forever? We're going to talk about time scales in a second. Of course, there is eventually a size of the Hilbert space, which might mess around with whether or not things grow exponentially, but there are saturation times, which I'll get to in a second. So just quickly, ensembles that we're generally interested in physics, these are random matrix ensembles. That is the Gaussian orthogonal ensemble. Those are real symmetric matrices. Gaussian unitary ensemble, those are complex Hermitian matrices, so things like Hamiltonians. And then sometimes people are interested in these Gaussian symplectic ensemble, which we're not interested in at all, which is the Hermitian quaternionic matrices. So getting on to basically Ephraim's question here, we can talk about different timescales in chaotic systems. There's tons of interest in them. One of the important timescales is early growth. So this is where the OTOC yields a Lyapunov exponent. I've just taken this plot from this paper by Mauro Chulias and Lea Santos. Basically, it's plotting the survival probability as a function of time. And in this region here is where the OTOC itself would yield a Lyapunov exponent. But there's not a lot of universality, especially in the survival probability in this region. So to say, for example, your initial state will change this gamma here, which is related to this local density of states, or LDOS as it's called. And this kind of power law decay also depends on the system. So it's not entirely universal. But there are some universal features that will show up later in time. And this is the region we're going to be interested in a little more in this talk. And that's this Phalus time, starting with Phalus time, which is just defined as the time at which a localized initial state will spread across a many-body Hilbert space. And that occurs, that's at the bottom of this this feature called the correlation hole. It's a manifestation essentially of the level repulsion in chaotic systems. And then you've got this thing called a ramp, which it ramps up basically, and it ramps up towards the relaxation time. And that's basically an estimate of when things like an OTOC perhaps, or some kind of observable will reach their long-term value, which is predicted by random matrix theory. So it's this region back here that we're going to be interested in, mostly in this paper. So the system that I'm going to be considering here is a two-mode Bose-Hubbard model, basically BEC and a double well. And it's going to be connected, it's going to have hopping term mediated by a two-mode impurity that we're calling it atomic quantum dot. And you can basically break down the Hamiltonian into three pieces. So you have the bosonic part, which is described here. You have these ON matrices, which describe self-interactions, so interactions between the bosons themselves. You have a hopping term, which governs how the bosons hop between the two wells. And then you've got a tilt term, which biases the bosons into one well or another. Basically, in this kind of central hump, we have a dot mode, or a atomic quantum dot, and it is trapped, and it has two levels. And essentially, you couple this boson dot, the bosonic system, with the dot, and it basically tunes the hopping parameter, because it's coupled to the SX term in the Hamiltonian. Most notably, the Hamiltonian H is not chaotic. And that's because the bosonic Hamiltonian itself, this is integrable. And then these dot modes, these dot part of the Hamiltonians, do not exchange energy. So when you're, in one mode of the atomic quantum dot, you're staying in that mode for the rest of the dynamics. And then here's just a couple examples of where, bosonic Josephson junction controlled by a single trapped ion. This is basically examples of where a Hamiltonian like this, or exactly this one specifically, is used. What we're going to be looking at is this order n two-time correlation function. So what this is essentially a generalization of the OTOC itself. So you have your object. This C is just the out-of-time ordered commutator, and the OTOC is this F. So we're calling it F2. And we're going to be measuring the kind of generalization of that on the qubit impurity itself. This, notice that there's no comma, so this is not a commutator. This is just W of t v0 repeated a bunch of times. And OTOCs have been discussed a bunch, especially so kind of more recently in the context of whether or not it can diagnose quantum chaos. And then also in information theory, people who study black holes and ADS CFT, in holography, they study these quite a bit. Okay, so I just want people to remember this picture for a second because it might become obscured. Just remember that this system is actually what's the system we're studying, because it's probably going to become a little bit obscured in the next slide. So looking at this object, this two-time correlation function, we'll select the atomic quantum dot operators W of 0 and V of 0 are sigma x. So they act only on the quantum dot. What we can do is we just find the time dependence of this sigma x, because that's the W, and you sandwich it with the time evolution operator. And what you can do is essentially use properties of Pauli operators, which means that when you're sandwiching the time evolution operator with the Pauli operator, you flip the signs of some of these sigma z's in the Hamiltonian. And then what pops out is this. And this, what it looks like is essentially the survival amplitude of a system which is undergoing dynamics with two different Hamiltonians. So basically what ends up happening is you have a shaken bosonic system, because now note that Hamiltonian 1 and 2 do not contain any of the operators on the atomic quantum dot. There's no sigmas, it's just the big ON matrices. So what this looks like is you're evolving forward in time with a bosonic Hamiltonian, where its hopping is frozen, and then backwards in time with a bosonic Hamiltonian where it's allowed to hop, and then doing this n times. And so this is what it effectively looks like, but don't forget the fact that all this is a two-time correlation function on a system which inherently is not chaotic. It just looks like this shaken system. But what we can do is we can look at things like Lyapunov exponents, for example. So if we look at the mean field versions of Hamiltonian H and Hamiltonian H1 and H2, and we can see that if we were to just look at H, unsurprisingly, we don't really get a Lyapunov exponent because it's not chaotic. But if you were to look at the shaken system, just the bosons that are going back and forth in these two Hamiltonians, you see a Lyapunov exponent start to emerge. And so this is done with respect to plotted with respect to the boson interaction. But perhaps more interestingly, you can plot it versus time. Or I've used capital T, but capital T is essentially just the time at which you're measuring this OTOC. And you find that if you measure this at short times, you don't get a Lyapunov exponent, but if you measure it at longer times, the shake period effectively increases and a Lyapunov exponent emerges. And that time scale is order 1, and we're going to kind of relate that to maybe some of the time scales we talked about before. What's really going on here? Well, what's effectively going on is you have this shaken system, you're evolving it back and forwards in time. If you keep the shake dynamics with a very short time scale, essentially you're getting trapped in some region of phase space. So this is a number difference, the bosons and again, this is classical, so phase difference. And you get trapped in a small region of phase space. But if you allow the time period in which you're measuring this OTOC to be longer, you are no longer trapped. You're allowed to hop between different energy surfaces, and you basically cover phase space. So this is n equals 50, and we've just, in units of the hopping energy, we've just said t equals 5, and longer, this is going to cover more of phase space. Okay, so those are classical signatures of chaos, but what about quantum? So the first thing I talked about with quantum signatures of chaos was correlations of level statistics, or level correlation. And we can't quite do that with this system because we don't have one single Hamiltonian, we have two. But what we can look at is the eigenphase correlation. And that's, I can imagine I have this time evolution operator, it's F for flow K, and I look at this and I see, okay, what are the eigenphases? So the eigenenergies modulo 2 pi, and is there any correlation in that? And at short times, what you can do is you can just look at what the effective Hamiltonian is for this system at short times, and turns out that at very short times, it's just Sx. And so we see very regular straight lines coming out of zero, and then around, things start to wind around the 2 pi, and then eventually things start to get a little chaotic in that you start to see eigenphase repulsion show up. And it may look like some of these lines cross, but I can assure you that none of them actually cross. They're actually just dancing around each other. And so at short times, you basically have a regular dynamics. And then at longer times, you get this eigenphase repulsion as these higher terms are included. And eventually this series is not really well defined in that sense. We can characterize this. And so that's, I mentioned that this is related to whether or not we're in a Wigner-Dyson or a Poissonian distribution. And rather than plotting it itself, which would involve something called unfolding the spectrum, we can characterize it using this thing called the average spacing ratio, R. And that is basically we take two phases and we find the difference between them. And then we find the next difference. So we get two gaps essentially and find the ratio between two adjacent gaps. And then you sum them all up. And this is kind of used all the time in studying whether or not a Hamiltonian is, Bayes random matrix theory and is therefore chaotic. And as it turns out, at short times, we get the Poissonian value of RP, which is down here just below 0.4. But again, something happens, and then after a certain amount of time, the random matrix theory kicks in, and we essentially get a ramp up to a chaotic value of R, the gap, and for longer times, it basically just oscillates around this value forever. Okay, so then now the last major things I'm going to be talking about is the survival probability and something called the inverse participation ratio. So you remember that this Fn, what it looked like was the survival amplitude of a chaotic system. Well, if I square it, then it becomes the survival probability of a system which is shaken back and forth. And what I can do is I can sum over some basis psi. So basically, whatever I'm measuring my OTOC with, my state psi, I'm going to average over some basis. And this is pretty common when you're studying chaotic systems. Most of the features that come out of especially random matrix theory show up when there's a lot of averaging going on. But essentially, what ends up happening is if you average this quantity over an entire basis, it turns out that this is related to something called the inverse participation ratio of instantaneous eigenvectors, these VJs, of the Floquet operator, this time evolution operator. And what that is just this overlap to the 4. And since F is time dependent, then VJ is time dependent. And so you get this time dependent quantity, which will start off at some value and eventually saturate to some other value. And then the long-term value is related to the ensemble that we're looking at. So we can look at what's actually happening. So in these first two panels, basically what we've taken is this OTOC, and we're measuring it for this first panel is using the basis of the hopping operator. This is Sx. And here I've just picked a random operator. So you fill a matrix with random values, you do a QR decomposition, and then you've got a random set of orthogonal bases or orthogonal eigenstates. And you can see that what ends up happening is it starts off, as it turns out, it starts off around order n, and then I'll elaborate more on this dashed line, but after this, around this dashed line, these insets are just log-log plots. You saturate to some value, and the red line here is this IPR CUE, that is the inverse participation ratio, which is predicted by the circular unitary ensemble. And that's about 1.967. And we get a pretty close value of this dashed line of 2.1. And for the random ensemble, it's actually quite it's quite astounding how well it does just for a random basis. I see I have 5 minutes, so that's good. As it turns out, in the SZ basis, you introduce another symmetry, which might seem a little funny in that this quantity depends on the basis that you're measuring. But remember, it's an OTOC, and depending on what object or what state I'm using for my OTOC, the value is going to come out. It will be state dependent. And so it actually, there's an extra symmetry that falls out, and you're actually in the circular orthogonal ensemble. And it's not quite as good, but it is better than if you were in the circular unitary ensemble, and you get fairly good agreement after some time. So just this last slide is to kind of highlight this time. And so what is this? Well, this is the Phalus time. This is the object timescale that I mentioned before. That was when random matrix theory starts kicking in. And so you can really see it when you don't average over the basis. Basically, you take individual states and you just look at them. They're more sensitive, and so the kind of long-term average values are not quite as good. But essentially, and that's for reasons to do with the initial state, but essentially, you have some short time behavior, and then after the Phalus time, basically when random matrix theory kicks in, this object is now going to start obeying chaotic statistics, and then you're going to get this kind of lots of oscillations around these long-term values that are predicted by random matrix theory. And it happens in both the circular unitary ensemble and the circular orthogonal ensemble. So that's about it for me right now. I just want to summarize what we did. Basically, we started with a non-chaotic system, this BEC in a double well with hopping mediated by an atomic quantum dot. And if we were to measure a generalized version of the OTOC, so the higher order version of the OTOC, basically what it ends up happening is it looks like the survival probability of a shaken system. And you can look at all these different signatures of chaos that people like to measure in chaotic systems. So classical examples were the phase-space trajectories and the Lyapunov exponent that came out of those. And then in the quantum case, we found eigenphase repulsion. We found a spacing ratio that agreed with the random matrix theory, and same with the survival probability. And then you can calculate the Phalus time exactly in these cases. All right, that's it for me. Thanks very much. And I'm happy to take questions if there's any questions.
Thanks, Wyatt. There's a question in the chat already. Is the Lyapunov exponent 0 in the mean field because it keeps the correlations to minimum and thus no chaos? Or is there another way to understand it?
Because it keeps the correlations to a minimum and thus no chaos. Are you referring to the correlations in the spectrum? Like there's no like level repulsion?
Okay, hi.
Hi.
So based on my understanding is that when you use the mean field theorem and you keep your correlations to minimum, like so isn't that what you did here when you got the effective Hamiltonian?
Yeah.
Or like okay, so when you get the effective Hamiltonian using the mean field theorem, you kept the correlations to minimum, and when the correlations is minimum, that means like somehow there's no chaos? Or like am I missing something?
Sorry, I'm not entirely understanding. So I'm just not sure which correlations you're talking about. So to get to the mean field equation, mean field Hamiltonians, you're using some Schwinger boson representations, and then you're replacing those with complex numbers essentially, and you're allowing basically these n's to take any value and the phases to take any value. So the number difference between these objects take any value. So what correlations? I'm not sure I understand.
Okay, I'm still like I was still studying the mean field theory like a week ago, so I'm not an expert.
Okay. Yeah.
Okay. So what I understand is that when you get an operator, you get like the expectation value, and you say that the expectation value is like the main thing, and all the deviations from this expectation value is minimum. Okay, and that's what I understood. And what I understood also is that the correlations between functions, what kind of correlations that what makes maybe the deviations more, what maybe makes, I really don't understand exactly what correlations is, but does the mean field theory in any way destroys or makes the system non-chaotic? If that's like a better phrasing for my question.
Right. Okay. So essentially, right. So okay. So there's a couple things to pull apart here.
Like,
one of which is that there's both of these are mean field. So like for example, H, the original Hamiltonian, this is just putting in the mean field version of H, whereas H1, H2 is putting in the mean field version of H1, H2, which are here. So they're both mean field, but I guess the step 2 mean field is to basically say that there is like, I guess n gets very, very large, and then there's some number of particles in the system get very large, and then your deviations from that are not, you're basically allowing, you're allowing and the number of bosons in the wells to get very large, and you're allowing this quantum dot to be just like a regular classical spin. So there's no deviation away from its classical expectation value.
Okay.
If that makes sense. And so I wouldn't say that changes whether or not it's chaotic. These are just kind of preliminary classical arguments, and then we kind of go into the quantum arguments. Of course, I haven't shown any eigenphase correlation or anything like that for the other non-chaotic model, but that's because I guess you have two systems and it's a little more complicated to discuss that. I hope that's sufficient.
Thank you.
Well, there was a question in the chat to me,
okay,
but I'm going to punt it to you, which was, you're measuring a Lyapunov exponent in a non-chaotic system. What's going on? So maybe you need to reiterate the main feature about what OTOCs are used for commonly.
Right. So OTOCs are pretty commonly used. So okay, this goes back to my first slide here. Is the OTOC itself is used to define a Lyapunov exponent in the quantum case, but also the Poisson bracket. And so in the classical diagnostics of chaos, I would measure a Lyapunov exponent through these definitions. So I would have some kind of trajectories that evolve in time, and then I average over phase space, do it a bunch of times, and then you can get the sense of the trajectories diverging. And so, but when you take it to quantum mechanics, you also do the same thing with the OTOC. But we're saying essentially that generalizing the OTOC rather than being an F2, you generalize it to Fn. And people do this. If F2 yields a Lyapunov exponent, or might not normally yield a Lyapunov exponent in a non-chaotic system, Fn might look like it has a Lyapunov exponent when really it shouldn't.
So if we were to digitize some continuous dynamics and put it on with a bunch of quantum gates, this is the kind of thing we could fall into. This kind of
exactly, yeah. So digital quantum simulation falls into this trap in that if you wanted to, digitize if you wanted to represent some operator with two operators that are being turned on and off, you fall into this trap of after the Phalus time, basically you are no longer in this regime, but quantum mechanically, you're now in this regime. And so depending on the length of your digital quantum simulation, I guess, pulses or whatever you're doing, you would run into signatures of chaos. And that's actually done in discussed in which paper here, the CBER paper, where they discuss a very similar idea of this digital quantum simulation. You get Trotter errors, and this trotterization of some kind of dynamics is what gives you this sort of behavior, looking through the lens of chaos in this case.
All right. Thanks again, Wyatt. Awesome talk. Now is our 30-minute